Vision language models, or VLMs, can perceive the world, understand language, and reason about what they see. So they have the fundamental capabilities needed to act as agents in visual and interactive environments. A great way to evaluate VLMs in this capacity is through video games, because they're interactive and have explicit rules. So a key question then is, can VLMs play games? And it turns out the answer is no, they cannot. This graph shows how VLMs barely perform better than random baselines in all but the simplest of games. And so our project will explore this gap to better understand why VLMs fail at game cognition, and hopefully the insights that we derive can guide researchers toward improving these models for interactive settings, like embodied AI and UI applications. In terms of related work, game-based benchmarks consistently show that VLMs fundamentally struggle to play games. A key gap is that these benchmarks mainly focus on assessing gameplay and task performance. So there's been limited insight into the failure modes that contribute to this poor performance. As a result, we plan to address this gap by developing systematic tests for diagnosing failure in game understanding. In particular, we have identified perception as a major source of error behind the poor performance, because errors in perception cascade to all downstream tasks like reasoning and rule application.
To systematically diagnose these failures, we propose a two-stage framework that isolates perception from reasoning. Stage 1 tests perception across 3 levels: low-level encoding, spatial processing, and high-level cognition. This outputs cell-level accuracy, showing where perception fails. Stage 2 requires verified perception. Models must fully understand the game state to enter the reasoning test cases. Stage 2 evaluates rule following through 2 layers. Test 0 establishes pure reasoning baseline without chess rules. Test 1 introduces chess rules and measures application accuracy across both spatial rules like piece movements and temporal rules requiring move history. So we began stage 1 investigating where the offset errors stem from encoding artifacts. First, patch alignment showed minimum effect across different models. Second, resolution divisibility indicated model-specific patterns. The QN3 favored non-standard resolution, while Gemma and Llama remained stable. Both test cases eliminated encoded artifacts as the root cause. So the stage 1 continues with spatial and cognitive experiments.
Models excel at pure temporal reasoning, achieving at least 97% accuracy. But when we ask them to apply temporal rules, performance drops dramatically, 7 to 53 percentage points. But spatial rules cause only less than 3 percentage points. So what's going wrong? We found models lack systematic rule verification when casting requires checking 6 conditions simultaneously. Accuracy drops to around 37%, but with just 2 conditions, it jumps to 90%. More critically, we found perception reasoning dissociation. The model correctly observes a pawn move 1 square during verification, then judges it as en passant, which requires 2 squares. Models see the facts, but don't apply them. They are pattern matching, not systematically verifying conditions. Can scaling solve this? No. Our 235 billion model only improved 10 percentage points over 8 billion model, despite being 29 times larger. Temporal rule integration requires architectural innovations, not just scale.
Given the unique nature of this research project, we have established 2 specialized evaluation metrics. The test implementation rate represents the percentage of completed tests relative to the total number of planned tests. The diagnostic yield indicates the proportion of tests yielding meaningful outcomes, either helping to identify the root cause or to eliminate a wrong direction. Our validation methodology has 2 key approaches: reproducing results under identical test conditions and validating findings across multiple experimental models. And over the next 3 weeks, we will continue executing our planned test protocols, following by convergent diagnostics, which is to analyze test results to identify potential common root causes across different experimental outcomes. After this phase, we will complete validation procedures and finalize the research report.